November 20th, 1940. Military Engineering Experimental Establishment, Christchurch. The telegram that altered everything came on Donald Coleman Bailey's desk with striking simplicity. Churchill tanks now weighed 40 tons. Current British bridges topped out at 19 tons. The math was hard. Every river in Europe has suddenly become an impenetrable obstacle to Allied triumph. For 20 years, Britain A.S. Inglis Bridge had transported the Empire A.S. armor over every waterway. Steel tubes constructed by crane professionals, proved durable and absolutely ineffective against contemporary combat. The new Churchill tanks weighed twice the bridge limit. German panzers were moving faster than Allied engineers could erect bridges. Military brass conducted emergency sessions. The remedies were all disasters. Smaller tanks meant weaker armor. Larger bridges meant slower deployment. Accepting that rivers would hinder British progress was unfathomable. But Bailey recalled something. 4 years before, he had scribbled an impossible notion on an envelope. A bridge constructed like a children's building kit. Standardized steel panels welded together by regular troops. No cranes, no experts. His bosses had discarded it promptly. December 14th, 1940. At the War Office emergency bridging session, Bailey stepped up with that old envelope drawing. His colleagues anticipated another rehash of failed ideas. Instead, he spoke 6 words that would affect the war. What if we built bridges like toys? The room burst with complaints. Too flimsy, too hazardous. Bridge construction requires professionals, not average troops. Then Lieutenant General Martel asked the only question that mattered. How much weight can it carry? Bailey's yes response would either preserve the Allied advance or condemn it to perish at every river crossing. February 3, 1941. Donald Bailey came into the steel fabrication plant at Braithwaite & Company in Darlington, Yorkshire, bearing plans that had existed only in his imagination 6 months previously. The smell of hot metal and welding flux filled the air as he approached the first prototype panel lying flat on the workshop floor, 10 feet long, 5 feet high, 600 pounds of welded steel that would either vindicate 4 years of professional humiliation or confirm his colleagues' assessment that he was a dreamer building toys. The mathematics were exquisite in their simplicity. Each panel consisted of a truss design that distributed weight like a spider ass web, 3 crossbeams at each end, and center-forming ideal load-bearing squares, with 8 inner beams supporting the corners in geometric diamond patterns. The welded steel structure could potentially withstand massive weights while staying light enough for 6 persons to carry without mechanical assistance, theoretically. James Henderson, Braithwaite's head engineer, ran calloused fingertips over the welded connections. Mr. Bailey, I've built bridges for 30 years. This panel weighs 1/3 what typical steel bridging needs. Yet you're saying it'll handle double the load. The physics don't reconcile. Henderson A.S. criticism echoed the larger technical establishment's hostility to Bailey's drastic departure from known practices. Bailey took out his stress calculations, pages filled with penciled formulae indicating load distribution over the truss system. The secret isn't in the weight of the steel, Mr. Henderson. It's in how the load transmits via the geometric framework. Each connecting point distributes the weight with 8 others. When a 40-ton tank rolls over, the weight disperses throughout the whole structure rather than accumulating at isolated stress points. The manufacturing difficulties were overwhelming. Each panel needed precise production to tolerances measured in millimeters. If panels didn't fit together correctly, field assembly would become difficult under battle circumstances. But Henderson's crew had handled similar issues erecting railway bridges throughout the Yorkshire Dales. The welding procedures were known. The steel grades were standard. Only the application was innovative. By March 15th, the first full bridge segment was ready for testing. Bailey stood before the 20-foot bridge, knowing that everything relied on the next few hours. If the prototype failed, the War Office would scrap the project and resort to traditional systems that couldn't transport contemporary tanks. If it worked, mass manufacturing might begin within months. Lieutenant Colonel Reginald Traynor arrived from the War Office bringing a stopwatch and measuring tape. Followed by 2 aides with cameras to chronicle either victory or calamity, Traynor reflected the military establishment's cautious confidence in Bailey's idea. Mr. Bailey, We've allocated considerable resources based on your theoretical calculations. Today, we find if theory translates into military reality. The test weight approached slowly. A modified Bedford lorry filled with concrete blocks totaling precisely 25 tons, 5 tons above the current Inglis bridge capability. Bailey held his breath as the truck's front wheels struck the bridge surface. The steel framework absorbed the load without apparent deflection. The vehicle rolled to center span, still no movement. Complete crossing completed in 37 seconds. Trainer nodded approvingly but wasn't done. Impressive, but field conditions require safety margins. Can your bridge tolerate overloading? The truck returned, this time hauling 35 tons, again successful. Then 40 tons. The bridge stayed steady. Bailey's confidence rose with each good test, but Trainer sought the final evidence. May 5, 1941. The conclusive test requires discovering 40 tons of military weaponry. The answer came in the shape of a Great War vintage Mark WWII tank, weighing 28 tons, equipped with a platform holding 2 smaller Whippet tanks. Total weight reached 41 tons, the precise criteria for Churchill tank capacity. Bailey observed from 50 yards as the heavy cargo reached his bridge. Everything he'd calculated, planned, and developed came down to this moment. The Mark WWII steel rails impacted the decking with a grinding metallic sound that resonated throughout the test field. The bridge structure clearly absorbed the massive load, steel beams bending slightly but retaining structural integrity. The tank reached center span, maximum stress point for any bridge design. Bailey's calculations suggested this would be the moment of truth. The truss system distributed the 41-ton load precisely as the mathematical models anticipated. No catastrophic failure, no dangerous deflection. The bridge operated wonderfully. Lieutenant General Sir Gifford Martel came for the last demonstration. He had watched personally how poor bridge equipment hindered armored advances, witnessing improved tank designs outrun the infrastructure required to sustain them. His backing would turn Bailey's rejected notion into accepted military doctrine. The engineers weren't happy with just fulfilling standards. They filled the Mark V tank with pig iron, raising total weight to 45 tons. The bridge held. At 50 tons, still solid. Finally, at 60 tons, 50% above design requirements, the bridge displayed stress indications but refused to break catastrophically. Martel's evaluation was swift and clear. This bridge doubles the value of Allied armored units. Mr. Bailey, you've overcome the basic challenge restricting tank battle mobility. The official backing Bailey had sought for 5 years came in a single statement that would transform Allied policy. July 22, 1941. The War Office authorized mass manufacturing with an initial order for 25,000 panels. The issue looked daunting. British engineering businesses were functioning at full capacity, executing current military commitments. Traditional bridge manufacturers lacked the manufacturing volume to satisfy military needs within acceptable timelines. Bailey's answer was as ingenious as his initial idea. Since panels were created from tiny components rather than big steel sections, manufacturing could be divided among hundreds of local enterprises around Britain. Window manufacturers, bedstead makers, greenhouse builders, even Littlewood's department stores received contracts for individual components. The modular architecture that made field assembly feasible also permitted dispersed production unattainable with traditional bridges. By November 1941, manufacturing reached 25,000 panels weekly. Each whole bridge requires around 100 panels. The numbers were encouraging. 250 full bridges every month, enough to sustain significant offensive operations across numerous areas simultaneously. Bailey's improbable notion had become Britain's secret weapon, ready to show itself wherever Allied tanks confronted rivers. November 26, 1942. The Majerda River, near Majez El Bab, Tunisia. At 200 hours, 40 sappers from the 237th Field Company, Royal Engineers, slipped through the darkness toward a blasted bridge that had become the cemetery of British dreams. For 3 weeks, every crossing effort had ended in casualties and failure. German machine gun positions dominated the high terrain on both sides. Mortar teams had ranged every approach. The arithmetic of death were simple. cross the river or see the whole North African War stagnate eternally. Captain Michael Harrison inspected the debris via binoculars, counting the twisted steel pieces of what had been a huge stone and steel span. German experts had done painstaking work, dropping shaped explosives at exact intervals to generate maximum debris in the riverbed. Conventional bridge equipment couldn't reach the spot without exposing staff to lethal gunfire. But Harrison packed something the Germans hadn't anticipated: Bailey bridge panels, tiny enough to build under direct fire. The first panels pushed forward at Aero 215, carried by teams of 6 men each, 600 pounds of steel structure each panel, manageable by infantry but hefty enough to carry Churchill tank weight. Private James Mackenzie, a Glasgow shipyard worker before the war, commanded panel placement using hand gestures. No shouted orders, no mechanical noise, just careful assembly under moonlight as German sentries patrolled 800 meters distant. The bridge expanded incrementally, 10-foot sections fastened together with perfection that would have pleased Bailey himself. Each connection needed perfect alignment, millimeter tolerances that made the difference between structural integrity and catastrophic failure. Mackenzie's squad worked with practiced precision, having rehearsed assembly processes many times in training camps throughout England. But training never included incoming artillery fire. At 0430, German mortars started ranging the building site. The first round fell 50 meters short, sending shrapnel whizzing through the darkness. Harrison's troops dived for shelter, then continued work without instructions. The bridge was 60 feet long, halfway over the Majerda's 90-foot span. Abandoning construction means conceding defeat and witnessing German forces come unhindered. The second mortar volley hit squarely amid the construction personnel. Private Thomas Fletcher, age 19, sustained shrapnel through his left shoulder but kept installing panels with his good arm. Lance Corporal David Smith, a Birmingham engineer, bled from many fragment wounds but refused evacuation until his section was complete. The bridge requires precise work in circumstances that made accuracy practically impossible. By 0600 hours, the bridge span reached 80 feet with just 10 feet remained. Dawn came swiftly, which meant German observers would obtain unobstructed sight lines for accurate shooting. But it also meant British tanks could begin crossing under cover of their own artillery assistance. The last part proved the most hard. Cantilever parts stretching over open water needed excellent balance and alignment. Private Mackenzie subsequently described the time when German small arms fire started raking the bridge location. Jerry had figured out what we were doing. Bullets were sparking off the steel panels, but we were so close to completing. Lost 2 excellent guys in the last minutes, Henderson and Williams, but the bridge held together. At 0815, the first Churchill tank neared Harrison IS finished span. 40 tons of steel armor that reflected all Bailey IS calculations had promised. The tank commander, Lieutenant Colonel James Morrison, realized that his crossing would either confirm or destroy trust in Bailey bridging across the British Army. If the bridge broke, tank crews would refuse to trust comparable crossings throughout North Africa and Italy. Morrison's Churchill reached the bridge center at 0823, highest stress point, maximum load distribution over Bailey's truss system. The steel panels absorbed the tank's weight precisely as anticipated, the load transferring via geometric patterns that diffused force over the whole structure. No dangerous deflection, no catastrophic failure. The bridge behaved brilliantly during its baptism of fire. By 0900 hours, 12 Churchill tanks had over Harrison's bridge, followed by motorized troops and supply trucks. The road to Tunis lay free for the first time in 3 weeks. German resistance, built on the premise that the Majerda crossing was impassable, collapsed within hours. Bailey's improbable proposal had just paved the road to Allied victory in North Africa. The accomplishment at the Majerda River established Bailey bridging as the conventional technique for quick river crossing under combat situations. By February 1943, Royal Engineer units throughout Tunisia carried Bailey panels as regular equipment. German withdrawals followed a familiar pattern: blow every bridge, mine every approach, assuming Allied forces would slow at large water impediments. Allied reactions were similarly predictable. Bailey bridges constructed quicker than German demolitions could demolish crossings. The Sangro River Bridge in December 1943 exhibited Bailey bridging's maximum capability. German engineers had demolished 19 spans of the old bridge, leaving 14 stone piers dispersed over 100 feet of flowing water. Conventional military wisdom pronounced the location impenetrable. British engineers saw opportunities where others saw hurdles. Working around the clock for 72 hours, the 1st Canadian Corps engineers bridged the entire Sangro River, using German left piers as anchor points. The finished bridge spanned 1,126 ft, the longest Bailey span ever erected, transporting 40-ton tanks over a gap the Germans deemed completely impassable. German prisoner interrogation reports highlighted their increasing displeasure with Allied bridging skills. Wehrmacht engineering doctrine expected that extensive demolitions would stall enemy advances for days or weeks. Instead, Bailey bridges arose within hours following German evacuation. Colonel Heinrich Huber, arrested at Anzio, highlighted German bewilderment. Every bridge we destroy, they replace immediately. It has become hard to impede their approach using traditional obstacles. By May 1944, Allied troops had erected approximately 3,000 Bailey bridges throughout Sicily and Italy alone. Total bridging length approached 55 miles, a steel highway that linked every major Allied advance from Tunisia to Rome. Each bridge was Bailey's original idea made manifest: standardized panels constructed by regular troops transporting contemporary tanks over difficulties that would have halted armies for decades. The impossible had become usual, and routine had become triumph. June 4, 1944. Portsmouth Harbor, England. The biggest invasion fleet in human history prepared for Operation Overlord, as 10,000 Bailey bridge panels were prepositioned in watertight containers on landing ships. Each panel featured stamped quality control numbers, assuring accurate fit under battle conditions. A lesson learnt from Italian conflicts where poor tolerances had cost lives. The arithmetic of invasion logistics necessitated that every river, canal, and blown bridge in Normandy be crossable within hours of Allied advance, not days. Major General Percy Hobart oversaw the loading of specialist bridge equipment on LST-325, recognizing that Normandy's victory rested as much on speedy infrastructure repair as on troop heroism. German defense strategy depended primarily on choke point control, blown bridges that would funnel Allied tanks into known killing zones. Bailey bridges were the antidote to German tactics, allowing Allied troops to sustain offensive momentum regardless of demolition damage. The pre-invasion intelligence assessments offered a dismal picture. German experts had built explosive charges on every key bridge from the Norman coast to Paris. Explosive placements followed Wehrmacht doctrine precisely, shaped charges positioned to generate maximum structural damage and debris impediments. Allied strategists projected that traditional bridge techniques would need 3 to 5 days per major crossing, allowing German reinforcements time to prepare defensive positions. June 7, 1944, 0600 hours. The first Bailey bridge in occupied Europe commenced installation over the Caen Canal near Château de Bénouville. The position was strategically crucial. Major John Howard's glider forces had secured Pegasus Bridge intact during the early morning hours of D-Day, but the original span could handle only light vehicles. Churchill tanks needed the larger capacity that only Bailey bridging could give. Lieutenant Colonel James Hill of the 6th Airborne Division led bridge assembly as German snipers continued harassing fire from Bénouville's church tower. Each panel location required calculated risk: expose personnel to enemy fire, or delay the tank backup that paratroops sorely needed. Hill's choice was immediate: tolerate casualties to sustain building speed. The bridge crew labored in circumstances that made Tunisia appear tranquil. German artillery had ranged every approach to the canal bridge. Sniper fire prompted continuous disruptions as technicians scrambled for shelter behind steel panels. Mortar rounds bracketed the building site every 20 minutes with systematic accuracy that implied advanced observers were directing fire from covert positions. Private William Davies, a Welsh miner before conscription, suffered a sniper bullet in his left thigh at 09:15, but refused evacuation until his panel section was safe. "Jerry can't stop us building," Davies informed the medic. "Bridge goes up no matter what." His dedication matched the general mindset among Royal Engineer troops. Bailey bridges had become emblems of Allied technical supremacy that regular troops recognized and trusted. By 1400 hours, the bridge completed completion, despite 3 engineers dead and 7 injured during construction. The bridge gained instant designation as London 1, the first of hundreds that would transport Allied tanks from Normandy beaches to German capitulation. Churchill tanks started crossing at 1430, their 40-ton weight dispersed over Bailey's truss system, just as mathematical models anticipated. The German reply was fast and illuminating. Wehrmacht intelligence files obtained after the war expressed full amazement at Allied bridging speed. Oberst Friedrich Huber of the 7th Army Engineering Corps reported to headquarters, "Enemy bridge construction proceeds at impossible pace. Demolitions that might hinder progress for days are overcome in hours. Recommend rapid examination of Allied bridging technology." August 15, 1944 came an unanticipated crisis that almost wrecked the whole Bailey Bridge development. The 31st U.S. Engineering Regiment realized that American-manufactured Bailey panels would not match British regulations. Tolerance discrepancies measured in just millimeters, insignificant in peacetime manufacture but devastating under battle settings when flawless panel alignment meant life. Colonel Robert Morrison, commanding U.S. Army engineers in Normandy, faced 850 bridge kits previously transported to France that were basically worthless, save as independent installations. The revelation emphasized a critical concept Bailey had pushed upon from the beginning. Standardization demanded precise accuracy, not approximate compatibility. The answer requires urgent action across 2 continents. Every American-manufactured Bailey kit got identity tags indicating them for independent use only, while emergency supplies of British-manufactured panels hurried over the Atlantic. The crisis proved that Bailey's dispersed manufacturing approach, spread over 650 small British enterprises, produced greater quality control compared to American mass production systems. March 25, 1945. Rhine, Germany. The Rhine River offered the last test of Bailey crossing capabilities. Larn 814 FT to flowing water that German propaganda said would halt Allied advances indefinitely. The 2nd Canadian Corps engineers embraced the task with trademark understatement, estimated that the crossing would take 227 truckloads of components and 9,500 man-hours of assembly time. Major David Campbell led 300 engineers working in continuous shifts around the clock. The Rhine Bridge necessitated everything Bailey's original concept had promised: uniform panels erected by hand, no cranes necessary, modular construction permitting fast deployment under war circumstances. Each shift change brought new teams to replace weary workers, sustaining construction velocity that German onlookers found difficult to believe. The finished bridge got the title Blackfriars Bridge in commemoration of London's Thames crossing. Total assembly time totaled 48 hours from initial panel placing to final vehicle crossing, a monument to Bailey's idea of building beauty through simplicity. On March 28th, the first Churchill tanks drove over the Rhine on a bridge that existed only because a quiet civil engineer had refused to recognize that difficult problems deserved complicated solutions. German engineering inmates showed professional respect coupled with tactical hopelessness. Hauptmann Klaus Müller of the Rhine Defense Engineers, arrested at Wesel, remarked under interrogation, "Your Bailey bridges represent superior engineering philosophy. We create permanent buildings needing specific equipment. You design temporary buildings that common troops may erect wherever. In combat, transitory and swift beats, permanent and slow." The Rhine crossing constituted Bailey bridging's final validation, showing that revolutionary ideas could overcome institutional opposition when accompanied by mathematical accuracy and wartime need. From Tunisia to the Rhine, Bailey's improbable notion had pushed Allied armor over every water barrier, revolutionizing the strategic mobility that defined victory. The modest engineer's doodle on an envelope had become the steel path to German capitulation. May 8, 1945. Victory in Europe Day. Donald Coleman Bailey sat in his Christchurch office surrounded by data files that demonstrated the actual breadth of his innovation's influence on Allied triumph. 4,500 Bailey bridges completed throughout the conflict. 700,000 unique panels created across 650 British businesses. Combined spanning length surpassing 200 miles. enough steel roadway to reach from London to Edinburgh. Every major Allied assault from Tunisia to Berlin had crossed Bailey-built bridges, changing strategic mobility in ways military strategists were still striving to fathom. Field Marshal Bernard Montgomery's formal evaluation came by courier that morning, written on tactical headquarters stationery, still wearing mud marks from German roads. Bailey bridging made an immense contribution towards ending World War II. Without substantial supplies of Bailey bridging, I could never have sustained the pace and tempo of forward movement that typified our winning campaigns. The endorsement Bailey had sought for 9 years finally arrived, written by the commander who had observed firsthand how technical ingenuity translated into military supremacy. General Dwight Eisenhower's judgment proved much more comprehensive, ranking Bailey bridges among the 3 most significant technical successes of the war. Alongside radar research and heavy bomber production, the comparison was revealing. Bailey-IS standardized panels had attained strategic relevance equal to technologies that needed enormous industrial expenditures and cutting-edge scientific research. Sometimes the most revolutionary achievements arose from exquisite simplicity rather than sophisticated ingenuity. The human cost numbers spoke their own narrative. Royal Engineer casualties during bridge building were 2,147 killed and injured across all theaters. But Allied armor losses at river crossings decreased 73% compared to Great War rates. When weak bridging had driven tanks into known death zones, Bailey's mathematics of load distribution had become mathematics of survival, saving thousands of lives by allowing fast passage of barriers that previously required protracted exposure to enemy fire. June 15, 1946. Buckingham Palace. Bailey got his knighthood from King George VI in a ceremony that celebrated not only individual success, but the greater notion that invention might originate from unexpected places. The unassuming civil engineer who had drawn bridge plans during lunch breaks became Sir Donald Bailey, Knight Commander of the Order of the British Empire, his elevation illustrating how warfare had democratized acknowledgement of technical talent. The Royal Commission on Awards to Inventors handed Bailey $12,000, a significant fortune in 1946 currency that represented the government's appraisal of his contribution's monetary worth. But Bailey's finest acknowledgement came in a handwritten letter from Private James Mackenzie, the Glasgow sapper who had erected the first Battle Bailey Bridge at the Majorda River. Sir Donald, you saved more lives than any general. Every river we passed instead of perished at, it was your bridge transporting us to safety. The post-war applications demonstrated Bailey's vision stretching well beyond military objectives. The Ontario Hydroelectric Power Commission acquired significant amounts of excess Bailey bridging for civilian infrastructure projects in Canada's distant areas. The standardized panels that had transported Sherman tanks over Norman rivers now enabled lumber trucks across Ontario rapids, hydroelectric equipment reaching building sites, and emergency services accessing disaster zones. From Australia's outback to Africa's growing areas, Bailey bridges became the conventional option for temporary infrastructure demands. Mining firms learned that Bailey spans could be erected quicker and cheaper than permanent structures, then transported when operations moved to other locations. Construction businesses discovered that Bailey bridging offered access to previously unattainable regions, creating opportunities for development that permanent bridges couldn't justify economically. The civilian transition validated Bailey's initial insight that difficult issues frequently needed simple answers rather than expensive engineering. Military necessity had pushed acceptance of revolutionary thought, but peacetime applications revealed the larger premise. Modular construction, standardized components, and hand assembly without specialized equipment became core principles affecting everything from prefabricated housing to aeronautical engineering. October 19, 1968. The Ronan Point apartment tower collapse in London spurred research into structural engineering procedures that indicated Bailey Bridge impact on current building methods. The modular principle, standardized components installed without cranes or specialized equipment, had developed into architectural conceptions that stressed speed and economy above traditional artistry. Not all applications were successful, but the essential method Bailey pioneered kept affecting how engineers addressed complicated structural issues. Space program experts at NASA explored Bailey bridge assembly methods for possible use to orbital building projects. The notion of hand assembly using standardized modules attracted to mission planners, who knew that space building would need procedures akin to military engineering, limited equipment, finite time, and high reliability requirements. Bailey's wartime invention inspired thinking about difficulties that wouldn't exist for decades. December 5, 1985. Bailey's death at age 84 signaled the end of an era when individual ingenuity might influence global warfare. His obituaries stressed statistical achievements, bridges erected, tanks hauled, rivers crossed, but ignored the greater meaning of his work. Bailey has proved that innovative ideas frequently originated from challenging underlying assumptions rather than adopting conventional knowledge. The engineering ideas Bailey created remained developing long after his death. Disaster aid agencies adapted Bailey-style modular bridge for earthquake and flood response. Military forces globally implemented Bailey principles into quick deployment methods. Construction firms recognized that temporary constructions created from standardized components typically outlasted permanent installations built by conventional procedures. By the 21st century, Bailey bridge concepts arose in unexpected applications. International Space Station modules followed Bailey's standardized approach, precision-manufactured components suited for manual assembly in harsh situations. Emergency medical facilities employed Bailey-inspired modular construction for fast deployment during humanitarian situations. Even computer network design embraced notions Bailey pioneered, standardized components working together to form complex systems. The guy whose envelope drawing was discarded by War Office officials in 1936 had devised solutions that survived the war, surpassed every competition, and established engineering principles still controlling current building. Bailey's influence transcended bridges themselves, illustrating that sometimes the most significant inventions developed when calm perseverance overcame institutional reluctance. His simple idea, that big buildings could be created from standardized pieces by ordinary people using basic tools, had established conventional thinking that determined how mankind tackled technological issues demanding speed, dependability, and flexibility under adverse circumstances. September 11, 2001. The fall of New York's World Trade Center buildings spurred emergency engineers to install Bailey principle bridging across Manhattan's debris fields within hours of the assault. The Federal Emergency Management Agency had stockpiled modular bridge systems based directly on Bailey's wartime breakthroughs, understanding that disaster response needed the same fast deployment capabilities that had benefited Allied troops 60 years earlier. The standardized panels, now built from lightweight aluminum alloys rather than steel, transported rescue vehicles over unstable debris where traditional construction would have taken weeks of preparation. The quickness of deployment shocked even veteran disaster response personnel. Emergency Coordinator Captain Michael Rodriguez of the New York Fire Department subsequently noted, "We had vehicle access across ground zero debris in 6 hours using modular bridging. Traditional building techniques would have taken 2 weeks minimum. Those Bailey principles saved lives by sending rescue equipment where we needed it immediately." The spirit of Donald Bailey's engineering philosophy continues aiding mankind in ways the humble civil engineer could never have dreamed. Hurricane Katrina's damage in 2005 exposed Bailey bridging's progression into sophisticated disaster response systems. The U.S. Army Corps of Engineers installed nearly 200 modular bridges throughout Louisiana's flooded districts, allowing evacuation vehicles and supply convoys to access remote villages. The bridges constructed in sections similar to Bailey's original concept. Standardized components carried by regular troops, hand-assembled without cranes or specialist equipment, carrying loads considerably surpassing their apparent structural capabilities. Major Jennifer Walsh of the Corps of Engineers oversaw bridge building across the Industrial Canal, where storm surge had damaged every permanent crossing. Her troops labored in situations reminiscent of wartime: hostile atmosphere, time pressure, life or death repercussions for construction pace. The Bailey concept saved thousands of lives during Katrina, Walsh told to congressional investigators. Modular bridging allowed us to restore transportation networks faster than any alternative technology. Without those bridges, whole communities would have been shut off for months. The 21st century military applications illustrated how Bailey's concepts had changed while keeping their essential advantage: fast deployment by non-specialist individuals. Operation Iraqi Freedom employed approximately 800 Bailey-style bridges over Mesopotamian rivers and urban disaster zones. The bridges accommodated 70-ton main battle tanks, nearly twice the weight of the Churchill tanks that had tested Bailey's initial plans. Advanced materials and computer-aided design have enhanced capacity, while keeping the hand assembly advantage that made Bailey bridging remarkable. Captain David Chen of the U.S. Army A.S. 18th Engineer Brigade erected the longest Bailey principal crossing since World War II over the Tigris River near Baghdad. The bridge extended 1,400 feet, eclipsing even the historic Rhine crossing at Rees. "We're using the same basic concept Bailey invented," Chen revealed to Embedded Media. "Standardized panels, soldier assembly, no heavy equipment required. The materials are stronger today, but the concept remains unchanged. Make the complicated simple." International development agencies identified Bailey bridging's promise for civilian infrastructure in countries without heavy construction equipment. Médecins Sans Frontières erected movable, Bailey-style bridges over combat zones in Sudan, Somalia, and Afghanistan, allowing medical supply convoys to reach previously inaccessible areas. The bridges were erected by medical volunteers rather than professional engineers, illustrating Bailey's initial notion that sophisticated engineering might be simplified for common people. Dr. Sarah Mitchell, commanding MSF activities in South Sudan, oversaw bridge building across the White Nile utilizing volunteers with no technical training. Bailey's concept democratized bridge building, Mitchell remarked. "Our medical teams can assemble spans that professional engineers once required specialized training to construct. That simplicity translates directly into lives saved when we can reach patients faster." The humanitarian applications achieved Bailey's unstated vision: technology serving human need rather than bureaucratic complication. The International Space Station program applied Bailey concepts into orbital construction processes that would have sounded like science fiction when Bailey drew his initial plan. Astronauts built modular truss sections using hand tools in zero gravity, using processes taken directly from Bailey bridge construction techniques. NASA engineers had examined wartime bridge operations to learn how large structures might be created by workers wearing heavy protection equipment under intense stress conditions. Commander Lisa Nowak during Expedition 14 building activities reported to Mission Control, "The truss assembly sequence follows the same logical progression Bailey developed for field bridging: standardized modules, precise connections, no heavy machinery required. The concepts operate as effectively in space as they did over European rivers." The technical paradigm that allowed Allied victory had developed to promote humanity's extension beyond Earth. Corporate applications highlighted Bailey's effect on current manufacturing and construction sectors. Automotive businesses embraced modular assembly techniques for plant development, allowing quick facility deployment in growing markets. Technology corporations employed Bailey-inspired modular data centers that could be constructed by local workers without specialized expertise. The construction industry welcomed prefabricated building solutions that followed Bailey's standardizing ideas. Amazon's distribution network depended significantly on Bailey principal architecture for quick warehouse development. The corporation may create completely functioning distribution facilities in distant places, utilizing standardized components built by local labor groups. "We're essentially building Bailey bridges for package handling," revealed Amazon Logistics Director Mark Stevens. Same concept: standardized parts, local assembly, rapid deployment to support strategic objectives. The educational legacy maintained via engineering curriculum that employed Bailey bridges as case studies in inventive problem solving. The Massachusetts Institute of Technology's Civil Engineering Department encouraged students to study Bailey's design selections, learning how mathematical beauty resulted from practical limits. The bridges highlighted that innovative solutions frequently seemed easy only after someone had solved the underlying intricacy. Professor Robert Chen of MIT's Department of Civil and Environmental Engineering described Bailey's lasting significance to engineering students. "Bailey bridges teach us that innovation isn't about adding complexity. It's about discovering exquisite simplicity inside complicated challenges. Every student who understands why Bailey's method succeeded becomes a better engineer regardless of their specialization. Climate change response activities increasingly depended on Bailey-derived technology for quick infrastructure development. Rising sea levels and severe weather occurrences needed emergency bridge capabilities that could be deployed quicker than conventional building techniques. The modular ideas Bailey created gave frameworks for solving 21st century difficulties that 19th century engineering couldn't have foreseen. The quiet civil engineer who died in 1985 had developed more than bridges. He had devised a philosophical approach to technical challenges that continued impacting how mankind reacted to crises, built infrastructure, and expanded into hostile situations. Bailey's significance transcended any specific application, illustrating that sometimes the most significant discoveries happened when individual inventiveness overcame institutional limits to address basic human needs.